Hello everyone, I'm Professor Harrison, and welcome back to our module on matrix algebra for finance. Today we're covering determinants, what they are and how to compute them, the key properties that come up most often, and the single most important thing a determinant tells you about a matrix, whether the system it represents has a unique solution. Determinants take a matrix and reduce it down to a single number, and that one number ends up doing a surprising amount of work. We're following Ruth, a former PhD student who just had her work stolen by a colleague. Armed with a new resolve to complete her work, she continues work from her apartment building on her own. She turns back to her dissertation. So far in this module, we built up matrices, the operations on them, and the procedure that takes a linear system all the way to a solution. Reduced row echelon form will always tell us whether a system has a unique solution, an infinite family of solutions, or no solution at all. But it requires actually running every row operation all the way through. What we want now is a single number we can compute directly from the coefficient matrix before doing any of that work. And that tells us whether the system has a unique solution or not. That number is called the determinant. The cleanest place to start is the simplest case, a 2x2 matrix. So Ruth's setup looks a lot like this. She is checking a small portfolio with two assets and two requirements. Asset 1 has an expected return of 10%, and asset 2 has an expected return of 2%. She wants a target portfolio with a return of 6%, and of course the weights have to sum to 1. So that gives her two equations and two unknowns. The unknowns are the weights on each asset. Before she actually solves for those weights, she wants to know whether the system has a unique answer, and the determinant is going to tell her that. The coefficient matrix on the weights ends up being a 2x2. The top row holds the return coefficients, and the bottom row holds the budget coefficients. And the determinant of a 2x2 is just one number. You multiply the top left by the bottom right, and then you subtract the product of the top right and the bottom left. So for a matrix that's a 2x2, and we have entries A, B, C, and D, we can go row by row, and the determinant is AD minus BC. Plugging Ruth's numbers in, that's 10% times 1 minus 2% times 1, which comes out to 0.08. This is important because we now know the determinant of the matrix is non-zero. So what exactly does that mean? Well, a non-zero determinant on the coefficient matrix means the system has a unique solution, which is exactly the question that she wants to have answered. The portfolio weights are uniquely determined, and we can solve the system. So what would it look like if the determinant came out to 0? Imagine for a moment that the two assets had an identical expected return, both of them 10%. Then both entries at the top row would be the same, and AD minus BC just collapses to 0. And that has a real interpretation. If the two assets have identical returns, then there's no way to uniquely determine how much to put in one and the other in order to hit your target return. Any mix of them is going to give the same answer. So the system does not have a unique solution. This is called the singularity criterion. When the determinant of a square matrix is 0, the matrix is called singular, and the system it represents either has infinitely many solutions or no solution at all. When the determinant is non-zero, the matrix is called non-singular, and the system has exactly one solution. So how do we compute the determinant of a larger matrix? Because real portfolio constraint systems are not a 2x2. As soon as we add more assets and more requirements, the matrix grows. The general procedure is called cofactor expansion. Sometimes it's also called the Laplace expansion after the mathematician who developed it. The idea here is recursion. We take a larger determinant and reduce it into a weighted sum of smaller determinants. A 3x3 reduces to a combination of 2x2s. A 4x4 reduces to a combination of 3x3s, and so on down the line. So you really only ever need to know how to do a 2x2. The cofactor procedure handles the rest. Let's see it on a 3x3. Suppose Ruth has extended her system to 3 assets with 3 requirements. The coefficient matrix is on the screen now. We are going to read off every single entry. We are going to then work through the procedure. So step 1, we pick a row or column. This can actually be any row or column. The smart move is to pick whichever one has the most zeros in it, because 0 entries are going to make whole pieces of the sum drop out. The first row of Ruth's matrix has a 0 sitting in the last position, so we're going to expand across the first row. Step 2. For each entry in that row, you build one piece of the sum. The piece is the entry itself, multiplied by the determinant of the smaller 2x2 you get from crossing out the row and column containing that entry. So 3 entries across the row gives us 3 pieces. Step 3. We add those 3 pieces up, but with alternating signs as you go across. The first one gets a plus sign and the second one gets a minus. The third one gets a plus. That alternating pattern is just a rule that comes from the procedure, and it continues across the rows no matter how big the matrix is. So going across the top row, let's calculate the determinant. The first entry is a 2. It is the first piece, so you get a plus sign. Cross out the first row in the first column, and you're left with a 2 by 2, which we call the minor. Its determinant is the same AD minus BC formula that we just used, and it comes out to 10. So the first piece is 2 times 10, which is 20. The second entry is a 1. It is the second piece, so it gets a minus sign. We cross out the first row in the second column. The leftover 2 by 2 minor has a determinant of 11. So the second piece is negative 1 times 11, which is negative 11. The third entry is 0. The sign would have to be a plus sign again because we alternate across the first row. But the good news here is that the entry is 0, so the whole piece is going to be multiplied by 0 and get canceled out. We don't even need to compute the last 2 by 2, and that's the payoff of expanding on a row that has a 0 in it. Adding the 3 pieces, 20 minus 11 plus 0 is 9. So the determinant of the 3 by 3 is 9, which we know is non-zero, so the 3-asset system must have a unique solution, just like the 2-asset version did. So that is the computation. We have a 2 by 2 formula, and anything larger can be done with cofactor expansion. Now there are a handful of properties of determinants that come up often enough that they are worth knowing on sight. There's 5 of them in particular. First, the determinant of the identity matrix is 1. The identity has 1s in the diagonal and 0s everywhere else. So AD minus BC is just 1 times 1 minus 0 times 0, which is 1. So the determinant of the identity matrix equals 1. Second, the determinant of a matrix equals the determinant of its transpose. Transposing flips rows and columns, and the determinant doesn't care which orientation you compute in. Third, the determinant of a product is the product of the determinants. So the determinant of A times B equals the determinant of A times the determinant of B. This is one of the most useful identities in matrix algebra, and we're going to come back to it. Fourth, if the matrix is triangular, meaning either all the entries below the diagonal are 0, or all the entries above the diagonal are 0, then the determinant is just the product of all the diagonal entries. So no cofactor expansion is actually needed. So if you can spot a triangular matrix, all that work disappears. And fifth, if you scale every entry of an n by n matrix by some constant c, then the determinant gets multiplied by c to the nth power. So scaling every entry of a 3-asset portfolio by 2 multiplies its determinant by 2 cubed, which is 8. The scaling is not linear because every row picks up the factor. So those are the 5 rules. Ruth gets up from her desk. She has built the test for whether her constraint system uniquely determines the portfolio weights, and she's finally finished this section of her dissertation. She has no committee on the other end of the page anymore, no advisors and no department to work with. Just her and her apartment with her desk in the framework. The methodology is going to get finished, and although she has no degree, she has no intention of stopping. So that is determinants. For a 2 by 2, the determinant is AD minus BC. For anything larger, you must use cofactor expansion. Pick a row or column that has as many zeros as possible, and multiply each entry by its sign and by the determinant of its minor, then add the pieces. The determinant of the identity is 1, the determinant of a transpose equals the determinant of the original matrix, and the determinants of a product is the product of the determinants. The determinant of a triangular matrix is the product of the diagonal entries, and scaling every entry of an n by some constant c multiplies the determinant by c to the nth power. 0 means singular and non-zero means a unique solution exists. One number per square matrix and a lot of leverage in it.